that's a good number. Okay, so starting off with the bell work. Share my screen real quick so you can see it. It says, in air, the speed of sound s in meters per second is a linear function of the air temperature T in degrees Celsius and is given by s of t is equal to 0.6 T plus 331.4. Which of the following statements is the best interpretation of the number 331.4 in this context? So in context, just understand that temperature is our input variable, and we get the air speed of sound, which is S, as it relates to the temperature. So looking at it, 331.4 is our constant. It would also be known as our y-intercept if you wanted to look at it that way. So in this context, since 0 degrees Celsius, when we plug that in, multiplied by 0.6, we're going to be left with just 331.4. So the correct answer choice is the speed of sound in meters per second at 0 degrees Celsius. So the correct answer is A. But if you're looking at some of the other answers, B, the speed of sound in meters per second at 0.6 degrees Celsius. Well, 0.6 is our slope, so that's what we're increasing per one temperature increase. So that one wouldn't really make sense of what 331 is. Answer C, the increase in the speed of sound in meters per second, that corresponds to an increase of 1 degrees Celsius. That is actually referring to 0.6 there. So if we increase 1 degree Celsius, we are no longer at 331.4, we would be at 332. And then looking at D, the increase in speed of sound in meters per second, that corresponds to an increase of 0.6 degrees Celsius. Once again, they're just trying to get crafty there, using the slope, trying to confuse you. But since it's the constant in our form y equals mx plus b, 331.4 is the y-intercept. So that's always our y value at 0. So we're going to be okay. Give me a second before we get going. I got to check on one of my kids in my cohort. Keep your head up. Pay attention to your class, dude. Put your phone away. What? Okay. Don't just sit there like that. You can be productive during this time, right? All righty. So like I said, today we're going to be talking about inverse relations and inverse functions, more specifically inverse functions of given functions. So we're going to find those algebraically. It's very process driven. If you stick to the process, you'll be okay. But it can be a little tricky at times. And then I wanted to talk to you guys about what you can expect for the rest of the week. Today you will have homework. On Wednesday, what you will have is you'll have a self-evaluation. I am not lecturing, but then you will have your midterm exam. Okay, your midterm exam will be about 50 questions at 1 point a pop. So it'll be about 50 points, roughly in there. And you will have until Monday morning to complete it. So in other words, it is retaking or is taking your mastery check as the midterm exam. It will cover everything that we've covered so far. Okay, so you'll go back and you'll do operations with complex numbers. You'll have the quadratic formula in there. You'll have all of the items from section 1.1 all the way through section 1.7, which we're going to be talking about today. It should be pretty, if you've done good on your mastery checks, you should do pretty good on this. Okay, it should not be hard. If you want to schedule a Zoom time to have a little help before the midterm exam, feel free to shoot me an email and we can get one set up. All right, but now we're off to lecture because we did our self-evaluation last week in our advocate for ourselves and catch-up day. So first, we're going to be talking a little bit about review. So we're given f of x is equal to 3x and gx is equal to x squared minus 1. It wants us to find what f times g of x is and the domain. The key thing when you're looking at the domain, like I said in lecture last week, last Monday, I like to find the domain afterwards. You can find the domain here, and it's really just taking this domain of 3x and combining it with the domain of x squared minus 1. So 3x is a linear function. So linear functions continue on without end unless they're restricted, like in a piecewise. So the domain there is all real numbers. G of x is x squared minus 1. That is also quadratic or a parabola. So once again, the domain's all real numbers. So as you can tell from our answer choices, our domain is going to be all real numbers as we go through. Now we just got to multiply them together. So first, they want you to set it up. So f times g of x is equal to f of x times g of x. Okay, just making it fancy. Then we can plug in. So 3x is equal to f of x. We're going to times that by the quantity of x squared minus 1, which is representative of g of x. So here we've used the distributive property. Oh, we just got to take this 3x times both. 3x times x squared gives you 3x cubed. 3x times a negative 1 is a minus 3x. So our answer is 3x squared, or 3x cubed minus 3x, which corresponds to answer selection B. Wednesday. Wednesday is the midterm. You will have until Monday to complete it. Okay, but you'll see an activity because you guys will still have your self-eval on Wednesday. Okay. So once again, we just multiplied it across. Make sure you're using the distributive property to multiply that 3x by both terms. I need to click back on the PowerPoint so that my little clicker works. And you can see that the correct answer is answer B. Next one, number 2, given f of x is equal to 3x and gx is equal to x squared minus 1, find f divided by gx and its domain. So this is one of those ones, it works better if we do the operation first to find the domain, because in all reality, both of these equations have a domain of all real numbers, like we just discussed. But once we put it in a division state, right, we can't become undefined. So it makes more sense if we find the domain afterwards. So we have trying to find f divided by g of x. This is equal to f of x divided by g of x. Okay, and then we just plug it in. F of x, once again, is 3x. G of x is x squared minus 1. And the only limitations that we have on domain is that this function in the denominator cannot equal 0. Okay, so let's think to ourselves, what number squared is going to be equal to 1, so that when we subtract it, we get 0, right? 1 minus 1 is 0. In this case, x cannot equal 1, because 1 squared minus 1 is equal to 0, and x cannot equal negative 1, because negative 1 squared is 1, minus 1 is equal to 0. So looking at the limitations in our domain, it shows that our correct answer should be D. There we go. There we go, there we go. All right. Here we go. Now we got a good one, where we're finding g of f of x. So this is composition of functions, okay, and domain. So once again, we begin with the knowledge, knowing that both of these equations have all real numbers. and we want to find what g of f of x is. Okay, in order to do that, remember that we first want to write out what g of x is. G of x is equal to x squared minus 1. Okay, and we want to plug in the function, the entire function of f of x into anywhere that an x occurs in g of x. So g of f of x is equal to 3x squared minus 1. Okay, in this one, the square applies to both terms. So 3 squared is 9, x squared is x squared minus 1. This is a polynomial, it's a parabola once again. So our domain should be all real numbers, and our answer should be A in this case. Number 4, okay, this is decomposition of functions. I didn't get a touch on it last week in lecture, but I did post a video about how to look at it. So essentially, it's given us h of x, which is equal to taking f of g of x, right? So what that means is that f of g of x is the composition, and when we do that composition, we're left with 2 divided by x minus 5 plus 1. Okay, there's multiple ways that we could end up getting this. Okay, there's multiple ways. The key thing is they just don't want us to use the identity function, which is that f of x is equal to x. So we want to think about these and determine which one could we really break out and make so that when we do the composition, we'd end up back where we started. So it's kind of reversing the process. Okay, and on this one, we can find the answer just by analyzing some of our equations. So for the first one, letter A, says that f of x is equal to x plus 1 and g of x is equal to 2 divided by x. Okay, so if we were to plug in f of x, we would end up with, if we were to plug in f of x into g of x, we would end up with 2 divided by the quantity of x plus 1. Okay, if we carried out that composition. But if we're plugging g in for x in the f of x, we have 2 over x plus 1, so that really doesn't get us where we need to go. Okay, looking at B, we have f of x is equal to 2 divided by x plus 1. So in this case, if we were to plug in g of x in for x, we would have 2 divided by the quantity of x minus 5 plus 1, which gets us back to where we started. That's probably our best option so far. Looking at C, we have x minus 5 and g of x is 2 over x. So once again, we're going to plug g of x into x in f of x. So we're going to have 2 divided by x minus 5. Doesn't get us back to where we started. And then D, 2 divided by x minus 5, and g of x being x plus 1. So if we plug g of x in for x, we would end up with 2 divided by the quantity of x plus 1 minus 5. So once again, that does not get us where we need to be. The only answer that actually restores it is answer B. So we're going to say that our correct answer is B. So in decomposition of functions, just imagine splitting it apart, but in order to truly check yourself, you got to put everything back together to make sure you end up what you started with. All right. So what we did last week was we found composition of functions and we did operations with functions, okay? Carrying out addition, subtraction, multiplication, and division. So if you remember, addition and subtraction is all about combining like terms. Okay, they both center around just combining the terms. Remember that when we're combining like terms, we can't combine an x squared and an x cubed. They have to be the same variable. with the same exponent, and then we would just adjust the coefficient. When you're talking about multiplication, it's a lot of the distributive property or FOIL. And then when you're talking about division, it's a lot of just rewriting it back over the top, putting the two functions into what honestly looks like a fraction with a numerator and the denominator. But then you also have the limits and domain. Most of the time, if you have a polynomial function, it's all real numbers, unless you are dividing, because then you can end up with an answer that makes your function undefined. So now what we're going to cover is we're going to use the graphs of functions to determine if they have inverse functions. Okay, and that's through a process called the horizontal line test. And then we're going to find inverse functions algebraically and graphically. Okay, and the key thing is we're not talking about inverse relations, we're talking about inverse functions. Okay, every relation has an inverse, but only certain functions have an inverse function. Okay, and the first way that we tell that, inverse relation, that's more or less just switching x and y, and you'll see that. Inverse function is a special type of inverse relation that passes the vertical line test when it's graphed. Okay, or each x value has one and only y value once it's been taken the inverse. And 1-to-1. Okay, 1-to-1 means that one item of the range matches exactly to one item of the domain. So you're going to hear this test. We know what the vertical line test does. That determines if we have a function. To determine if we have an inverse function, we use the horizontal line test. And if a function passes the horizontal line test, that means, one, that it has an inverse function. Okay, so when we take the inverse, it turns out to be a function. And two, that each item in the range corresponds to one item of the domain, or one y value for every x value. Okay, and it's a specific y value. It's unique. So just knowing that, if you consider a parabola, since it always is those U shapes, if you were to draw a horizontal line that intersects that graph, we would intersect that graph at two places, unless we drew one so exact and we barely touched the vertex of that graph. So horizontal line test. A function f has an inverse function. Okay, once again, we're not talking inverse relations, we're talking inverse functions. Inverse relation just means that we switch the x and y values. Okay, we switch what is the dependent and independent variables. So a function f has an inverse function. F inverse is expressed just like that, f with the -1 on top. If and only if each horizontal line intersects the graph at most one point. Okay, this is an example of a 1-to-1 function. Wherever we were to draw this graph, and I know it looks like it levels out here, but it really doesn't. It's still decreasing as it approaches 0, or as x approaches -infinity. That horizontal line intersects that graph one time at one point. Okay, so since no horizontal line intersects the graph f more than once, the inverse, f inverse, exists. Okay, or the inverse function. Once again, it's not an inverse relation. Every relation has an inverse, because all that means is that we switch our x and y's. We're talking about inverse functions, which is a special type of inverse relation. Okay, so that when we find the inverse, we will have a function in itself, and a function being that it can pass the vertical line test. So the first problems that you're going to have is really just graphing it and drawing a horizontal line, or estimating what a horizontal line would look through. Okay, I think that's like your first 5 or 6 questions on this homework assignment. So we're going to need Desmos, we're going to need graphing calculators. So graph the function 4x squared plus 4x plus 1 using your graphing calculator and apply the horizontal line test to determine whether its inverse function exists. right? Yes or no? So honestly, we could answer this question without having to graph it. And that's because we know what graph shape this should be, right? The parent graph to this would be x squared, okay? So x squared gives you a parabola. Any type of parabola is always a U shape. So since it's always a U shape, when we draw a horizontal line, we're going to intersect the graph twice. We can identify that straight from the equation. Okay, and that's because it's in the standard form, ax squared plus bx plus c. It's a quadratic. We know it's a parabola. But we'll amuse ourselves, and we're going to go to Desmos. What is it? It is 4x squared minus 4x, 4x squared plus 4x plus 1. So we go to our Desmos app, 4x squared plus 4x plus 1. Okay, that's what our graph looks like. And you can see just using the grid lines, like if we were to use 2, for example, here, we were to draw a horizontal line, you can see that it clearly bisects the graph at 2 points. And what this means is that when we were to take the inverse, we would not have a function. Okay? And some people would say, well, we could just take the square root. You really could, but the square root is limited in domain, being that you can't take a square root of a negative number and get a real number. So the square root function is kind of an oddball in this case. But since this graph does not pass the horizontal line test, its inverse relation is not a function. So we would write no. Okay. Once again, it's not saying that there isn't an inverse relation. We're saying that the inverse is not a function. Okay, because we can take the inverse relation of anything, because that's just switching x and y. But we're looking for inverse functions, which is a special type of inverse relation. So our answer to this question would be no. Okay, graph the function x to the 5th plus x cubed minus 1. Clear that out. So x to the 5th minus x to the 3rd and a minus 1 at the end of it. Okay, so here, looking at this graph, this is what we get. Once again, Desmos is very helpful because if we use the grid lines, you can see that we're okay down here. Down here, it kind of passes the horizontal line test. It also passes it up here, but it's this part right here that causes us the problem. Okay, you can see that we intersect the y value of a -2 once, twice, 3 times, 4 times. Okay, and we only need to intersect it more than once to make sure that this is not an inverse function. So we would say no in this case as well. That's false. Unless I plugged it in wrong. Oh, I had it minus. You guys didn't. Dang it. Okay. -1. Missed it by decimal points. Once again, that just shows you got to be detailed. You can see that just this plus right there, I had it as a minus at first. You can see what that graph did. This one definitely doesn't pass, right? But when I actually put it in the way it's supposed to be put in and not make a mistake, you see this one's a little tough here because it looks like we kind of come horizontal at -1. So this is where your trace function really comes into play. So if I click and I drag on this, and this is just because graphing is an estimation, you can see I'm at -0.094, -0.063, -1.048, 0.036, 0.017, 0.008, -1. Now I'm above it. So at first examination, this is honestly the problem with graphing. Graphing is always an estimate, right? So we really got to, and to save us from having to plug in each of these points, we can use Desmos if we use the trace function. That way we don't have to find it algebraically. But on second examination, even though we're off by decimal points, we still wouldn't be able to draw a horizontal line that intersects this graph more than once. Okay, and that's kind of the problem with the horizontal line test, is that you got to break it down into its smallest points. Okay, even though they're super close, -1 and -1.000001 are two separate numbers. Okay, so this one at first glance really looks like we would, but if we zoom way in, okay, you can kind of see that we're off by milliseconds, millions. Okay, so this one would pass the horizontal line test. And we can conclude that this one would have an inverse function. So don't be afraid to zoom. Don't be afraid to zoom in. Don't be afraid to use your trace function, especially if it looks like that graph at the first glance. It's one of those confusing ones, right? Don't be afraid to zoom in. Don't be afraid to use the trace function. If you're using the TI-83, once again, that's just by hitting trace. And then you can actually arrow across, or you can plug in individual X values to make your life simple. That way you don't have to plug in 0.0001 into this equation. Okay, so graph the function f of x is equal to 3 divided by x minus 1 using a graphing calculator. Apply the horizontal line test to determine whether its inverse function exists. Right? Yes or no. So 3 divided by x minus 1. So we'll graph it first. 3 divided by the quantity of x minus 1. Double check myself, that way I don't look like an idiot again. Here we go, zoom out to get a picture of it. So looking at it, this one also a tough one because we have this in behavior. We can clearly see that it passes here, but as we go farther and farther left, you can see how it looks like it gets very close to 0. But what we have to understand is that 0 is going to be an asymptote, so we're never going to touch 0. And that each of these y values changes all the way down to a millionth. Okay, so since it changes, okay, and it doesn't truly become level, it is decreasing as we go. And you can see my y values keep changing. So this one, we're going to say, yeah, it passes. And that's, like I said, graphing is just an estimation. So don't be afraid to use your trace function. Okay, now looking at our graphs, this is the right graph, but they have the wrong answer. D, completely wrong graph. B, completely wrong graph. A is the only one that has the correct answer with the correct graph. So we can say that this is answer A. So that's how we're going to treat the very beginning of our problems. Okay, a lot of graphing, a lot of estimating to determine whether we pass the horizontal line test or not. Like I said, do not be afraid to use the trace function. Okay, we have the technology and the capability to be able to do it. It would be very dumb of us not to use our capabilities. Okay, so when it comes to finding the inverse function, okay, like I said, an inverse relation is just switching the x and y values. Okay, we switch them. Find the inverse function. First, we got to determine whether it exists. So we want to do the horizontal line test at the very beginning all the time. Okay? And if it exists, then we can carry out and use the algebraic stuff. Okay? And then we'll do that algebraically. So step one, determine whether the function has an inverse by checking to see if it's 1-to-1 using the horizontal line test. So that's what we just did. Step two, in the equation for f of x, replace f of x with y and then interchange x and y. So there's the switch. Okay, we interchange x and y to make the switch. And then once we've made that switch, we're going to solve for y and then replace y with the f inverse of x in the new equation. Okay, and then step four, state any restrictions to the domain of f inverse. Then show the domain of f is equal to the range of f inverse, and the range of f is equal to the domain of f inverse. So in other words, we want to state any restrictions on the domain. Okay, and since we switch f of x and y, or f of x and x, the dependent and independent variables, the dependent variable in our first equation, okay, x turns into the range in our second equation. Okay, you got to picture it because we're switching our x's and y's and then we're solving. So the domain of our first function turns into the range of our second function, and the range of our first function turns into the domain of our first function. Okay, it's a fancy way to say that the x's of the first function correspond to the y's of the second function, and the y's of the first function correspond to the x's in the second function. And once again, that's because we switch them. We got to make that switch. Okay, determine whether f has an inverse function, f of x. So f of x is equal to x divided by 2x minus 1. So first thing, we'll graph it. X divided by quantity of 2x minus 1. Double check myself once again. Now I'm all worried. I hate making mistakes. Okay, once again, this is another one of those inverse, I wouldn't even call it, I'd call it the reciprocal function, where we have an infinite discontinuity here in the middle. And then we just got to remember that it's decreasing as we go to a negative infinity, or it's increasing as we go to a negative infinity, and it's decreasing as we go to a positive one. I know it looks like it levels out, but on closer examination, as we go farther and farther, you can see that my y values continue to decrease and my y values continue to increase. So this one does pass the horizontal line test. Okay, and once again, graphing, it's an estimation. Don't be afraid to use the trace function. Okay, it never constantly, or it never levels out. So yes, this one passes the horizontal line test. Okay, so now it's time to algebraically solve it to find what our inverse functions equation is. So step one, we've already passed it. Step two helps if we have the equation written down. So it's x minus 2x minus 1. Okay, they want us to plug y in, or replace f of x with y. Okay, once again, still on step two. Now here comes the switch. Here I have two x's, so I need to have two y values. So x is equal to y over 2y minus 1. And now I want to begin to isolate my y values. So first step, multiply this side by 2y minus 1, and multiply this side by 2y minus 1. So that gives me x times 2y minus 1 is equal to y. Distribute. Two xy minus x is equal to y. Okay, that's from distributing. Now I need to get this y value to this side. Okay, I'm going to do that by subtracting. So now I have 2xy minus x minus y. I need to get rid of this x. And that's equal to 0. So I'm going to plus x to both sides. And once I do that, I'm running out of room. I'm going to have 2xy minus y is equal to x. Okay, follow those steps. Can you guys see there's not a glare or anything like that? So I replaced them. I distributed. I brought this y over. I brought my x variable to this side. Okay, so I subtracted y, I plus x to just isolate it and to give myself a little bit more room. So I'm going to bring this to the top, which gives me 2xy minus y is equal to x. Okay, at this point, in order to finish this problem, I need to factor out. Okay, between these two terms, there's a greatest common factor. So I'm going to reverse the distributive property. The greatest common factor is y. So taking out the y, I'm left with 2x minus 1 is equal to x. Okay, needed to factor. Now I have y times 2x minus 1. So I can divide this whole side by 2x minus 1. I have to divide on this side at the same time. So I'm left with y is equal to x divided by 2x minus 1. And then to finish off my steps, f inverse of x is equal to x divided by 2x minus 1. Now I need to state any restrictions in the domain. Okay, but if I use my graph, it makes it kind of easy. If I use the original graph. So let me pull that up real quick. So if I zoom in here, you can see that I have a horizontal asymptote right there. Okay, here we're counting by 0.5s. And you can see my graph approaches 0.5, but it never touches it. Okay, that's a limitation on the domain or the range. And since I know, because I had to switch x and y, that's now a limitation on my domain of my inverse function. So that means that my graph cannot have x equal 0.5. Okay, cannot equal a positive 0.5. Can equal -1. And that, once again, because 0.5 is the only value, that would turn this undefined. 0.5 times 2 is 1, minus 1 makes 0. Okay, so your limitations. Okay, explain the domain, how I found it. That's what you talk about, Rosalind? Okay, so once again, that's totally fine. I'm happy you guys are asking questions. Let me know I'm not talking to myself. Sometimes I get worried about that. You know, I think that's a sign of being crazy, and I might be crazy, but just crazy enough to keep it interesting. But I'm glad to know I'm not talking to myself. So once again, from this slide, or from our key concept, I'll go back to it because it's a little bit easier to explain. Right here. Stupid. Right here. Step 4. Okay. So it shows that the domain of f is equal to the range of f inverse. So once again, the domain corresponds to all the x values. right? And our range corresponds to all the y values. So once we take, in order to find the f inverse of x, or the inverse of x, we had to switch those, right? We had to switch the x and y's, and then we had to solve, like we just did algebraically. So because we did that switch, and we had to solve, any limitations on the range of the original function, which is shown here, are now limitations on the domain of the inverse function. Okay, and just by analyzing my graph, I have two here. So these grid lines are at 0.5. And you can see if I go farther and farther to the right, it looks like it gets there, but it never does. Okay. If I go farther and farther left, it looks like it gets there. Like we approach it, we can definitely say that the limit as x approaches negative infinity and positive infinity is 0.5, right? The limit, we're close, but we're never going to truly touch it. So since these are limitations on the range, they turn into limitations on the domain of our inverse. And you can see it, I solved it, so I can add this. So this is what our inverse actually looks like. And you'll see oh, that's fun. 2x minus 1. Turns out to be the same equation. Here's 0.5, and you can see the purples overlap. It's one of those, that's why they call this the reciprocal function. The inverse is the same as the regular. But you can see we're never going to touch 0.5 in an x value. Okay, once we hit 0.5, that makes our function undefined and gives us that infinite discontinuity. So that's a limitation on the domain. So the graph passes the horizontal line test. That was step one. Therefore, f is a one-to-one function and has an inverse function. From the graph, that you can see that the domain of f has negative infinity to 1/2, the union of 1/2 to a positive infinity, and the range is a negative infinity to 1/2 with the union at 1/2 and a positive infinity. Now we got to find f inverse. This is them plugging it in. There's the graph. Okay, the original function, they replaced f of x with y. They switched it. Not normally. Not normally. It's just on these reciprocal functions. But not normally, Leah. Okay, the reciprocal functions have a higher chance, but this is just a special one. Interchange x and y. And then they begin to solve for y. So the first thing that they're going to do, they multiply it. Okay, then they isolate the y value by bringing it across. Okay, and then they factor. Exactly how I did, and then they divide. So y is equal to x divided by 2x minus 1. So the f inverse, this one, it just happened to turn out to be the same equation. And the limitation on the domain, 1/2, because that's what makes our function undefined. So like this one here, determine whether f has an inverse function. Okay, so once again, first thing we do, we want to plug it in and graph it. So 2 times the square root of x minus 1. So 2, there's my square root of x minus 1. Who's playing games? So here's what my graph looks like. You can see that it does pass the horizontal line test. If I zoom out, Okay, so we're good on step one. Passes the horizontal line test for 1 to 1. Now we got to go through our algebraic steps again. Okay, first step, we have f of x is equal to 2 square root x minus 1. Replace it with y. And then we want to begin to start solve for y. So in this case here, okay, I just rewrote y. Switch your variables. So x is equal to 2 times the square root of y minus 1. Okay, now I can solve for y. First step, divide by 2 on both sides. So I'm left with x minus 2 is equal to the square root of y minus 1. The only way to get rid of a square root is to square it. Okay, but I have to square both sides. So this in the numerator turns into x squared. 2 squared is 4. And that is equal to y minus 1. Okay, and then I add 1 to isolate my variable further. So I'm left with y is equal to x squared divided by 4 plus 1. Okay, so that is my inverse equation. Oh, I didn't finish it off. Last step is we got to write as f inverse of x is equal to x squared minus 4 plus 1. Doesn't materially change the question. It's just that final step because we're in function notation and they want us to put it as f inverse. So we did pass the horizontal line test. Okay, the original function, they replace f of x with y. They switch x and y. Then they divide each side by 2. Once again, to isolate the y variable. They square each side to get rid of the square root. Then they add 1 to completely isolate the y variable. F inverse of x is equal to x squared minus divided by 4 plus 1. Okay, it has a domain of positive infinity to a negative infinity. That's because the range on our last one was not limited. It's a parabola. There we go. Okay, compositions of inverse functions. Okay, this is kind of the last thing that you'll have to do. And more or less, so compositions, exactly what we did last week. So if they are truly inverse functions, once you take the composition, it'll be equal to just a single x. Okay, so two functions, f and g, are inverse functions if and only if f of g of x is equal to x for every x in the domain of g of x, and g of f of x is equal to x for every x in the domain of f of x. So more or less, once we compose them, if we were to plug these in, we would be able to prove that they're inverses because we would just be left with x. Okay, so this requires you to compose them. So show that f of x, which is equal to 2/3 x plus 2, and g of x was equal to 3/2 times the quantity of x minus 2, are inverse functions. So here they go. They're just doing composition of functions, exactly what we did last week. So on this left side here, this is the equation for f of x. Okay, and now they've plugged it in. They've brought g of x in. You can see once they distribute this, you're going to have 6 over 6, which is equal to 1. Okay, and then that's going to be x minus 2 plus 2, which leaves you with just x. And then on this side, here they have g of x as the equation. They've plugged it in for the x value. Okay, they've distributed across. And now we're just going to be left with x minus 2 plus 2, which is equal to x, and x plus 3 minus 3, which is also just going to be equal to x. Okay, so the key point is that when we compose these functions, we will be able to get just x. All right, so I'm going to go ahead and end lecture there. Okay, to give you guys a little bit of time to start this, that way I can be